So, good morning. This is a lecture on computer control. And if you remember, last week, I've presented a very simple example, yet quite realistic because it was motivated by a situation that, however, was simple, corresponding to an actual moving robot. And we could develop an algorithm, control algorithm for the position of the robot, and provide stability conditions, and even provide conditions for the movement not to have oscillations. And we could do that with very simple arguments. And one important thing that was a consequence of that example was that in computer control, you are working in discrete time, okay? And in general, the structure is the one that you can see on this slide. So you have a physical plant, which is continuous, and it's related to a computer via DA and AD converters. And what you want to do is to design a controller, which is nothing more than an algorithm that reads data from the input port of the computer connected to the AD converter and to the sensors that measure plant data. And this algorithm computes the value of the manipulated variables that you write at the output port, which is connected to the DA converter, and yields the command signals for the actuators. So the valves or the ailerons or whatever the actuators might be. The first part of the course will be about modeling in discrete time models. But before that, I would like to start this lecture by recalling a number of important notions from control, and also to explore a little bit some, sorry, some possibilities that are offered by the fact that you have a computer and you can write software to implement a control algorithm. So you can be very flexible in the rule that generates the manipulated variable, and consider situations like nonlinearities or time variations of the plant in a way which is, at least in principle, easy. Then, of course, you must be careful with stability and with achieving the desired performance issues. And you must remember that sometimes things are very plausible, but the heuristics not always works. You must rely on mathematical analysis. So from now on, I will discuss with you a number of features of control. These features are quite general. Not only they are common also to control in continuous time, and you have studied them. But let's remember these features. Okay, this is something that we have seen. The slides that I jumped, and now my question is: suppose that you want to control the impulse that you are giving to an aircraft. Okay, so you have a command to a motor, and this motor generates some impulse, and you want to keep it constant. Okay, so if you think about feedback control, which is a very basic control structure, what you do, you measure the impulse y, you compare it with a reference impulse. Okay, so r is the reference, is the value that you want y to have, and you build a tracking error e, and you, according to proportional feedback control, you just amplify it. Now the question is, does it work? I mean, does y approaches, suppose that you want to have a constant reference from the impulse. Thus, y approaches r. In qualitative terms, it's understandable. It's easy to see that it does not exactly go to r, because if y is exactly equal to r, then the error is 0, and the excitation of the motor is 0. So immediately the impulse is reduced. So what happens is that you need to have some error for the system to work, which is a little bit surprising, but you have studied these things, and you know what is the remedy for this situation. Can you think of the remedy? How should we change the controller to ensure that y goes exactly to r in steady state, apart from stability considerations, assuming that the closed loop is stable? What should we do to modify our controller such that y approaches a constant r? Can someone tell me in one word or two words?
We should use an integral controller.
That's perfect. We should add an integral. So what happens is that if we had an integral, we could use just an integral controller, but usually we insert the integral in parallel with a proportional action. Okay, and what happens is that if the error is 0, well, this term is not here, this proportional term is not here, the input to the integrator is 0, but the output is not 0, and should be, if things are okay, should have the value which is the excitation of the motor that is adequate for y to be equal to 1. Okay. Now let me ask you another question. Why don't we just put an integral and we add this term here, this proportional term here? Can someone tell me what is the advantage of this term, this proportional term in parallel with the integrator? You remember? Okay, I will give you a hand. Actually, we can think of two things. Well, one thing has to do with performance. If you add an integral, okay, the response of the integrator is slow because it goes on integrating the error, so it needs some time to reach the correct point. Okay, so if you just have the integrator, the response would be slow. Okay, instead, the response of the proportional term, this term here, is instantaneous with respect to e. Okay, so the proportional term gives you a quite fast response, but you have a long-term steady-state error, and the integrator responds in the long term and corrects that error. So if you had just integrator, you would not have any steady-state error, but you would have a very slow response. Okay, this is one thing that has to do with performance. Now, we should also remember stability. When you are adding poles in the feedback loop, you should be careful because when you do the feedback, the poles change their positions and they go to infinity or to zeros when you increase the gain. And they go to infinity, the ones that go to infinity, they can go to the right-hand plane. So you can have stability problems by increasing the gain when you try, for instance, to make the response of the system faster. So one thing that you can do is to create a zero that attracts some of these poles and prevents some of these closed loop poles and prevents them to go to the right-hand plane. And actually, if you think of 1 plus 1 divided by STI, well, TI is a constant, okay? what you are doing, the equivalent of the parallel of these two branches is a transfer function that has a pole at the origin in S, but has a 0, okay? And you can very easily do this summing, consider that. And this 0 is on the left-hand plane and attracts the poles of the closed loop and contributes to stability. So you can increase the gain and not have stability problems, at least in for very simple systems. Okay, now the general case. In the general case, we have a feedback loop that has these signals and systems. So you have your plant that I'm assuming it's linear, and it's modeled by transfer function G of S. And you have your controller, and in general, the controller has not to do just one, does not need to be just a proportional controller, can be a transfer function, can have a transfer function, can be a dynamic system. And so I call the transfer function of the controller K of S, okay? And then what you have the reference R, which is compared with the measurement of the plant output Y. But the plant output Y is measured with sensors, and sensors introduce noise. So V is noise, okay, which is additive noise, okay? So the reference is compared not with the true plant output, but compared with Y, the true output, plus observation noise of the sensor noise. And then you build this error and you amplify it with your controller K of S, and you generate the excitation to the system, U. So U is what you apply to the actuators, the signals, the command that you apply to the actuators. But now you have disturbances. You can model disturbances at the input or at the output, okay? I'm modeling in this case the disturbances as an additive signal to the input. For instance, if you have a moving staircase, uma escada rolante, okay? And you want the staircase to move at a constant speed. But now, when someone steps over the staircase, it's a disturbance. And the staircase must have a control system to keep the movement, to keep the speed constant. Because otherwise, when you put some load on it, there is clearly a resistance to movement, and the movement would tend to be slower. So you have to somehow compensate that by a feedback controller. So in an aircraft, if you have a wind gust, you can have disturbances of several types. A wind gust, uma rajada de vento, it's a disturbance. If you have a boiler and you are producing electricity using a turbine, and suppose that you increase suddenly the amount of electricity, the power that you are producing. So you need to extract more steam from the boiler, okay? This is a disturbance on the pressure of the boiler, okay? Because you are suddenly you started extracting more steam than what was happening before, okay? So you can find many examples of disturbances in systems. And actually, the idea is that the feedback system renders Y insensitive to W and V. So to the disturbances and to the sensor noise. Okay. Now, without doing any mathematics, you can see that we have a problem. And the problem is that you see V enters the same one the sensor noise V enters the same way as the reference that you want to track. So you could change this and have here delete V from here and add here R minus V. Okay, so the difference of R and V. So the system is not tracking Y, is not tracking the reference, but is tracking the difference of the reference and the noise. This means that we should be careful, and noise, sensor noise, pose a stringent limitation on the reference. Does anyone have an idea how we can tackle this problem of avoiding the noise effect when trying to follow R by Y? Alguém que tenha uma ideia de como é que nós podemos resolver o problema de termos ruído e o ruído afetar o seguimento da referência? Porque o ruído e a referência entram da mesma maneira. Anyone has an idea? Okay. Yes, Leonardo.
Fazer moldagem do ganho de malha, loop shaping.
Beautiful, okay? You should shape the gain margin, the gain margin of the closed loop system. Perfect, Leonardo. Okay, so and how should we shape the loop gain?
A low gain for higher frequencies and for lower frequencies a higher gain, so that kg over 1 plus kg is more or less 1 for lower frequencies.
Okay, apart from a small detail, that's perfect. In the low frequency, you don't want it to be 1. The loop gain is the product kg, and what you want to be 1 is the transfer function between R and Y. Let's see that in a moment. But apart from that detail, that's perfect, Leonardo. And I think that some of you remember this, some other of you do not remember. So let's look at some very simple mathematics. So let's compute the transfer function between Y and the signals that are inputs to this feedback loop. And we have 3 signals: the reference, of course, then the disturbance W, and the noise. Okay? So how can we compute this? We use superposition. So we compute Y, the transfer function between R and Y, assuming W and V0. Then we compute the transfer function between Y and W, assuming R and V to be 0. And the same for Y and V, assuming W and R to be 0. And then we add everything. This is what we have here, okay? And remember that, for instance, if when W and V are 0, when W and V are 0 and you have a feedback loop, what do you have? You have the direct transfer function, kg, divided by 1 plus the loop gain, which is kg times, if you had here some transfer function, you have to include it also, but now this is 1, so it's 1 plus kg, okay? Now, when you have R and V equal to 0, you look at the transfer function between W and Y. So now the direct transfer function is just G, and again the loop gain is G. Okay, so for the loop gain, what you do is you cut the loop at some place and multiply all the gains. Finally, for V, okay, now we have a minus here that you can move to this point, and so that's why it appears here, this minus. And you have V affects Y because it passes by K and G, divided by 1 plus the loop gain. Okay? Now, I wrote this formula here at the bottom of this slide. Suppose that you want Y to track R. So kg should be big, because if kg is big, then 1 plus kg is more or less equal to kg. So kg divided by kg is 1. Okay? So kg big, and kg is the so-called loop gain. Loop gain big implies y tracks R. Now, if you want to reject the disturbance, you want kg to be big, because if kg is big, then g divided by 1 plus kg is approximately 1 divided by k. K is big, so this is approximately 0. So up to now, we have kg big ensures tracking the reference and rejecting the disturbance. Now, for the noise, remember, you want to have kg small, because kg small implies that you have, say, a number close to 0 divided by 1, which is close to 0. And this conflicts with the requirement that kg is big. So the trick is to consider different regions of the frequency response. And usually in the low frequency response, where you have good sensors and V can be neglected, then you have a specification that tells you kg is above something, is big. It's above some shaded threshold, okay? Now, in the high frequency, where you have noise, you have to impose that kg is below some threshold, okay? Now, you can say, well, maybe I could, in this frequency range, where kg is big, I could, I have a good tracking of the reference, and I have also good disturbance rejection. So I could select the frequency limit of the band in which kg is big to be as high as possible. So instead of having this frequency in this point, I move it, say, to here. So I have a kg big, 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 and then it falls very fast because of the noise. Now, we have one problem that we should not forget, which is stability. And stability has to do with the phase, okay? And it happens that the phase depends on the inclination, on the slope of the kg, the loop gain curve. So if you have a very strong, a very fast decay of the modulus of kg in frequency, then the phase drops very fast and we have stability problems. That's a consequence of the Nyquist stability criterion, that is something that appears in your nightmares, okay? But for the moment, all you have to remember is that if you impose a very big, in negative terms, big slope, big, very fast decay of the loop gain curve, the phase drops very fast, and you have stability problems, okay? So actually there is a minimum frequency range between kg being big and kg being small, okay? And the whole story of control is here. The whole story of at least linear control is select k such that kg passes in this allowed region left by the specifications, okay? Any question about this? Okay, this is something that you should bear in mind, because control, this is the essence of control. Control is not just making some computations or putting a PID here or a PID there. You have to think globally in terms of performance and stability, and usually you have some trade-offs. And the whole picture is here. The whole story of control is here in this slide 52. Okay. Now, we have the equations for the PI. Okay. And first of all, what is the relation with PI? Why is PI so popular? What is the relation of PI and what I've just discussed in slide 52? Some ideas. Por que o controlador PI é tão popular e qual é a relação que há aqui com o slide 52? You can say that in Portuguese if you want. For instance, if you have just an integral control, what happens to the loop gain? Se tiverem só controlador, só controlador integral, if you have just one integral action controller, what happens to the loop gain? What is the frequency response of the integrator? In qualitative terms. What is the transfer function of the integrator? Qual é a função de transferência do integrador?
1 over S.
1 over S, okay. Now, how can you compute the gain of a system from the transfer function? What do you do?
We see when we increase the frequency, if it goes up or down, or isn't that?
I give you a G of S, for instance, 1 of S, okay? That's the transfer function. And how can you compute the gain of this transfer function?
We replace the S equals to 0 and we get the static gain.
Okay, that's the gain in one point, but now the gain has a frequency omega.
Okay, so in this case is 1 over J omega.
Okay, so
and omega is increasing, so the gain is decreasing.
That's right, okay? So you replace S by J omega and you take the modulus, okay? So in the case of the PI, as you said, the transfer function is 1 over S, that's 1 divided by J omega, so the gain is 1 divided by omega. So the loop gain is decreasing, S should be, okay? So if you force an integrator, you are going to have something that decreases in frequency, very high at low frequencies and very small at high frequencies, okay? Now, if you had the proportional action, you are adding a 0, and the 0 makes the frequency decay not to be so pronounced, so reduces the decay of the frequency of the gain in frequency, okay? So use it for the story of stability, okay? In this critical region where the gain is 0 dB or 1, the slope must be at most you can show it using a result known as Bode's integral theorem. It must be not bigger than 20 dBs per decade. Okay, so use the 0 to make the slope not much big, not to decay too much. Okay, so that is why the PI or some, if you have a PID, you are adding still another 0, so you have 2 zeros instead of just 1. Okay, and that's why the PI or the PID are so popular. That's one of the reasons, because they right from the beginning they force the loop, the shape of the loop gain to be the correct one, more or less, at least in some simple terms. So we have these equations. You compute the error, which is the difference between the reference and Y. Of course, You know that this is the measure of y, but let's assume we have no sensor noise. And then you compute the manipulated variable u, or the control variable, as a gain k, proportional gain, times the sum of the error and the integral of the error weighted by some weight. Usually people write this gain as 1 divided by ti, and ti is a constant, okay? That's intuitor time. It's a matter of convenience, okay? Sometimes in some books you see K1 and K2 and that's it. Now, if you want to have a digital version of this, you can do it in several ways, okay? U is the sum of two terms, the proportional term, and that's very simple because it's just a multiplication of a constant times the error, which is the difference of two variables. So these operations are very simple. But now, how can we approximate an integrator in a computer, okay? Now, you can do it in many, many ways. You had a course long ago on numerical methods, and actually you can use numerical methods for integration. Let's use a very simple one, okay? So one possibility is this one. So let's call ui equal to this term here. So 1 divided by ti, the integral of v, okay? Now, if I differentiate, what do I get? On the left, I have the derivative of ui, and on the right, I have the derivative of the integral, which is just e, okay? So by differentiating, I get this expression here. The derivative with respect to time of ui, remember that ui is this term, okay, as defined here, is equal to 1 divided by ti, which is a constant times e. Okay, now instead of an integral, I have a derivative, but I can approximate the derivative by the definition of derivative, okay? The definition of derivative is the difference of two close points of the function divided by the time between them, okay? So I take as h the sampling interval, and I have two consecutive samples of ui. There is an I missing here, I'm sorry, okay? So I plug this here, and I solve with respect to u of nh, ui of nh. So I end up with this expression. Now I leave the algebra to you, which is very simple, okay? It's very simple to see that ui of nh minus ui of n minus 1h divided by h is equal to 1 over ti e. Okay? So the PI, the digital PI is nothing more than you have the reference, it's in the computer, you can write it on the keyboard, and then you read y at discrete time n from the input port connected to the AD. Now you compute this intermediate value ui as the previous value plus this quantity, which is a constant, h divided by ti. H is the sampling interval times the error, the last error that you have computed there, okay? And finally, you add the two terms, ui, e, and multiply by the proportional gain, okay? So to implement this algorithm, what you need a position of memory to memorize the last value of ui, and some multiplication by constants and some summation of variables, okay? You can do it even with very low powerful computers. Actually, I did that when I was your age, and there was no MATLAB, and computers were scarce. It was very rare to find, and I did that in machine language. You can, well, actually assembly. I was assembling by hand. Virtually, I was programming in machine language, and I could program a PI controller. Okay. Now you can do it in C or Python or Pascal or whatever you want. Even in MATLAB, you can do it even in MATLAB. So this is the idea of presenting this algorithm is interesting in two ways. Well, first, it's a useful controller. Okay, actually, you need to add some extras for the PI, but okay, this works. If you program this, and it works in many cases. Of course, you have to design K, TI, and the sampling interval. Okay, the sampling interval is something that you have to be careful. Later, we will discuss the choice of the sampling interval. So the algorithm is as interest in itself. Perhaps more important than that is that this gives you the idea of what is a very simple computer control algorithm. Okay, we have seen last week we have seen a very simple algorithm which was just multiply by a constant, compute the error and multiply by a constant. Now you are seeing something that depends on the past values of the excitation to the system. So you have the algorithm has some memory of the past. Okay, and usually digital control or computer control algorithms have this structure. Okay, you must have some memory of past variables, and then you do some computations with them depending on the algorithm. Okay. Any question up to now? If you don't understand something that I say, please tell me. Okay. Sometimes my tongue gets around my teeth and so on, so I'm not so clear. So when you don't understand, you can even interrupt me and say, please, okay, repeat that better, okay? Repitam lá isso melhor, que eu não estou a perceber. Interrompam-me sempre que quiserem, tá bem? Any question? Okay, let's proceed.
Teacher.
Yes.
I had a question.
Yes.
If we use another another memory space to save another previous value of UI, do we gain something?
Yes, you can. Actually, it's possible to have systems for which you cannot even stabilize it with PI algorithm. Há sistemas para os quais que não são estabilizáveis com PI. It's not you cannot go too far. I mean, if you have a high order system and a system which is of order say 4 or 5, and this is quite common, you can find combinations of poles and zeros, such that if you use a PI controller, and no matter how brave you are in selecting K and TI, you are not able even to stabilize it. In some other cases, you can stabilize the system, but the best performance that you can get is not so good. Okay, so if you have more complex processes, you need to have more parameters to adjust, and you will need a further memory. Okay, I can give you a personal example. I was involved in the control or adaptive control actually of the steam temperature in a power plant, and later I will show you the results. Actually it was adaptive control, so the controller was changed, but basically it was something with the structure, and then we had some other algorithm adjusting the gains. And before we started working, of course the plant, it was a plant from EDP. They had design engineers, and they were quite brave engineers. They had a very bright person, and he had a control system based on PIs. Actually, there was more than one. And he was convinced that it was not possible to beat that. Now, we used a controller that had more complexity. So instead of having just one position of memory, in the past we had more positions. Of course, the algorithm is a little bit different from this one, but we were having more memories of the variables, of the plant variables in the past. Okay, actually much more, say 4 or 5 positions in the past, and we could improve the result, the error, by a factor of 3.5. Okay, so they wanted to keep the temperature still, so constant around 1 reference value, but the temperature due to disturbances was usually varying. Okay, and we could reduce the variations with respect to the use of network of PI controllers by a factor of 3.5 less, which is quite important because it has an impact on the money they could do with the electricity they were producing. Okay, that's another story. Okay, but it's quite important. Does it answer your question?
Yes, Professor. Thank you.
Later, we are going to see how we can do that. Okay.
Okay.
Of course, there is one expression which is kiss. Kiss means in Portuguese beijo, no? But kiss here means another thing. Keep it simple, stupid. Okay. If you are not a good engineer, you will tend to find complicated solutions. Okay, and that is not good. So always start from the simplest solution. If the simplest solution works, why should we use more complicated solutions? Okay, if you are improving your performance by 1% or 2%, what is the point of having a very complicated controller that then is very difficult to tune? Only a few people can. You need an engineer very specialized to tune it, and sometimes it does not work because it's so good. That's a story of robustness. Okay? So there's no point. If you don't have a significant improvement in performance, use the simplest thing. Okay, and the simplest thing always start with a proportional controller, then a PI controller. Okay, then a PID, and then move to other things. Okay, so it's a sign of being clever. The opposite of KISS, of keep it simple, stupid. The opposite is always try to use the simplest solution. Okay. Of course, in many cases, the simplest solution works. Okay? In many situations in industry, the dynamics of the processes is very simple. Then you have about, say, 5 or 10% in which you need much more complicated solutions to achieve your objectives or to improve significantly performance. And improving performance means that your employer is going to receive more money. Okay, that's the value of engineering. Okay? To use in a clever way the resources such that to earn money. That's life. And in those cases, you need more powerful situations. Now, in recent years, you see more and more small companies, sometimes not so small companies, but working in projects like underwater robotics or even normal robotics or mobile robotics or the space. We have a number of companies that produce, do design and have products for space. And in those cases, you need to have more sophisticated systems. Okay? But the idea is always try to use the simplest thing. If it does not work, then you progress. Okay, let's move on. Okay, so the pseudocode for PID digital is what I said I want to repeat. Now, let me let me speak a little bit about adaptive control, okay, which is concerned with the fact that you can exploit the advantages of having a computer and not just some fixed hardware where you do some multiplications or, okay? Now, suppose that you have a nonlinear actuator, okay? So you have your system. Let's suppose that your system is linear, and you have a nonlinear actuator. And the nonlinear actuator in this case is, it opens or it does an action which is proportional to the force power of the command. So when your controller applies a command which is U, then the actuator responds and applies to the system a stimulus which is U to the force. Okay? This is just a mathematical example, but actually you can find many of these situations. And we use a PI controller here, and we tune the PI controller. Now, let's see what happens. Suppose that you apply a step variation in the reference, but starting from different points of work. So you are at an equilibrium point, which is 0.2 or 3 or 5. And you see that at 0.2, the response is quite nice, okay? So you apply a step of 0.1, and it moves from 0.2 to 0.3 with a little bit of overshoot. Now, if instead of starting the maneuver at 0.2, if you start it at 3, then you have some oscillations, and this is no longer acceptable. And if you start at 5, it even becomes unstable. You see that the amplitude of these oscillations start to increase, okay? What is the reason for this? The reason for this is that you have the U, the actuator is U up to the force power. Now, the derivative of this is 3U to the cube. So when Y is bigger, U must be also bigger. And if U is bigger, the slope of the curve, which is proportional to 3 times U to the third power, increases. And this is an incremental gain. And the incremental gain, in this case, we have 3 poles, makes, if it increases, makes the system to be unstable. Okay? Now, so we have this problem. And this problem means that if you are working in one region around 0.2, everything is okay. But if you are working in other regions, you should have used another tuning of the controller. Okay? Now, how can we do this? You can do it in 2 ways. One way is we have a table. So the table changes the gain of the controller. And if you move from 0.2 to 3, you are going just to reduce the gain. And you know, if you know the characteristic of the actuator, you can differentiate it, and you know the increase in gain, so you reduce the gain. Okay, so use a table. Now you can say, well, this is a quite academic example, don't bother. Well, those of you who came by car, I'm sure that your car had this system inbuilt. Okay, so now virtually all the cars have a combustion control system, and the combustion control system does several things. And for instance, when you push the accelerator pedal, quando pisam o pedal do acelerador, once it was connected to a mechanical system injecting more or less gasoline in the motor. Now you are just giving a signal to a computer that controls the injection of gas and air. And the exhaust gas, they pass in a point where there is a sensor called the lambda sensor, and the lambda sensor measures the excess oxygen, okay? And the excess oxygen in the gas from the combustion that go out from the combustion determine the efficiency of the system, okay? So if you are adding too much air to the system, then the efficiency is low. But if you are adding too little air to the system, then you are just sending away unburned, unconsumed gas. Portanto, se a quantidade de ar for muito pequena, não há ar suficiente para queimar todo o combustível e estão por isso simplesmente a deitar fora combustível não queimado. Se o ar for excessivo, baixa a eficiência da combustão. Okay? So there is a range for the excess air which is measured by the so-called lambda sensor. And this signal is used by a control system. Now, the dynamics is quite nonlinear. So this control system has a table of gains for the controller that changes the controller gains depending on the conditions in which the car is running. For instance, if the car is running in a flat street, you have one controller. But if you are climbing a hill or going down a hill, use different other controllers. Okay? So depending on the conditions, on the variables, okay, and these variables are the consumption of the speed and the consumption of air, usually, depending on these two variables, you select different values of the controller gains. Okay? This is something called gain scheduling. Okay, gain scheduling. You can see here gain scheduling, which is nothing more than you have, for instance, in this case, 3 different controllers. Okay, one for small speeds, another for medium speed, and another for high speed. In a car, is even more complicated because, as I said, you have the air. Now, you multiply the output of these controllers by weights. So these weights are between 0 and 1. And this variable is the velocity. So this phi of v is a function between 0 and 1. Okay? For low values of the speed, this function is close to 1 here, and for high values is close to 0. Okay? Now, for intermediate values, for low values of v, it's 0. For intermediate values is 1, and for high values is 0. And the same for I. And then you add the outputs of the 3 controllers to build the control variable. So you are, in a sense, interpolating the 3 possible controllers. In a car, you have as much as 16 of different controllers for different combinations of the process variables. Let me give you another example. And this is shows the linearized model of an aircraft, and depending on the velocity, and this is the dynamics of the angle of attack. Okay, and as you can see, when you change the velocity, the speed of the aircraft, you are changing the position of the zeros, you are changing the position of the poles. These are all poles. Okay. here you have the poles at 15 meters per second, and at 35 meters per second, this aircraft, the pole was moving here. And also there were other poles moving here. Okay, so you have this effect of change. And this is a simulation in which you see that the velocity is increasing linearly, and you have a constant controller. And with the constant controller, for very low speed, you have some oscillation, you have some overshoot. Then the controller was designed more or less in this range of speed, so you have a good response here. At very high velocities, you have even an instability. Okay, so this is the type of thing in which you can use this story of gain scheduling. Now, gain scheduling is one possibility, but it's one possibility that requires that you know exactly how the system is going to work. Sometimes you have changes in which you don't know where they come from. They are unexpected changes in dynamics. So another possibility is that you have your feedback loop controller, and then you have an adapter, an adaptive system. And the adaptive system looks at the process variables, the manipulated variables and the output variables, okay? And does some computations to adjust the controller gains. The simplest case is when you have, you estimate a model for the plant and you redesign the gains of the controller in line. This is done in line. That's adaptive control. Okay, so this is just to give you two examples of what you can do when you have the power of a computer at your hand and you can start writing code. Okay? One limitation is that your algorithms may not be too complicated because you have to comply with the interval, with the sampling interval. And the sampling interval can be very small. And if your computations are too much heavy, then you don't have enough time to complete the computations within the sampling interval. So there is a limitation also with computer power. What is happening is that more and more you see very powerful computers. So the capacity of the computer controlled systems to run very complicated algorithms is increasing. At this moment, the European Space Agency is looking already for the possibility of incorporating artificial intelligence and machine learning and reinforcement learning algorithms in control problems for spacecrafts, just to give you an idea. At this moment, everything is quite conservative. With fixed controllers. Predictive control is something which we will speak about later in the course. There are some viability studies. I think that there are no implementations for the moment, at least in spacecraft. In cars, there are implementations. They work in cars, controlling car motion. And now you have the more complicated algorithms of machine learning coming. And the expectation is that in a few years, there are certified processors that are able to run very sophisticated control algorithms. Okay, this was what I want to tell you in this class. Let's make a quick review of what we said. The first thing was in computer control, what you have learned about, and sometimes forgotten, about the structure of a control system is still true. Okay, the frequency interpretation is a little bit different because you are now working with discrete time systems, but the ideas are still true. And then I tried to give you some idea of basic computer control algorithms. The most basic one is PI, which has an interest by itself, but I showed also to explain to you how we can write an algorithm, a very simple algorithm. Then I called your attention to this story of the possibility of having more sophisticated algorithms, in particular gain scheduling, which is a very powerful idea, connected to patching, colar controllers, patching controllers for different conditions of work or adaptive control. Okay? Now, what I will start to do tomorrow is to speak about models in computer control, which will be the base for design. So before we leave, any questions or comments? Okay, if not, I end here and we will resume tomorrow.
Professor, I have a question, sorry.
Yes.
Regarding the laboratory classes, is there a link available for today's classes, or will they only start later?
You are going to receive information about that. The classes will start in the week of the 12th of October. And what is important, what is really important is that you organize in groups of 3 or 4, okay?
Okay.
And the week before you will receive the description of the work to be done. And each of you will have will have 5 sessions. There will be later the possibility of selecting the sessions. We will open that. These sessions are online sessions. So part of the sessions will be tutorial, and some other part will be devoted to discussions with you if you have questions, or where you can pose questions about your work and so on. So it's not mandatory that you exactly attend those sessions in which you are enrolled, but we recommend that because the idea is to have some degree of interaction. If everybody goes to one session, then this is much more reduced. But you will receive more information later.
Okay, thank you.
Any other question? Okay, so we will see each other tomorrow, or at least you will see me, because I only see black squares with your names. It's already something, and I hear your voices. So bye-bye. See you tomorrow.
Bye, Professor.
Bye.
Thank you,
Bye,
Professor.
Professor.
See you tomorrow.